AI Podcast. I'm Ethan Park. Today we're unpacking a well-known research study from DeepMind called Training Compute Optimal Large Language Models, often nicknamed the Chinchilla Paper. With me is our listener, Maya Gupta.
Hi, Ethan. I've heard the name chinchilla a lot, but I'm not totally sure what changed because of it. I'm ready to learn.
Let's start with the takeaway so no one has to wait. If your training compute is fixed, the best results come from balancing model size and the amount of training data. In practice, that often means using a smaller model and training it on more tokens. DeepMind validated this by training Chinchilla with fewer parameters than their earlier model, Gopher, but on far more data. With roughly the same total compute, Chinchilla performed better across many benchmarks and is cheaper to run because it's smaller.
So the headline is smaller model, more data, better results at the same training cost. Got it.
A quick word on who did this. The paper is led by Jordan Hoffmann with colleagues at DeepMind, including Sebastian Borgeaud and Arthur Mensch. It first appeared on arXiv in 2022 and was later published at NeurIPS that year.
Thanks. Set the scene for me. What problem were they trying to solve?
Before this work, the community tended to scale parameters aggressively while keeping training tokens roughly constant. That meant many very large models were likely undertrained for the data they saw. The question the paper answers is straightforward but crucial. For a known compute budget, what mix of parameters and training tokens gives the lowest final training loss?
Right, because most teams get only one real shot at a full training run. If you choose the wrong size or training length, you've burned the budget.
Exactly. Prior recommendations often kept training schedules fixed while changing model size and measured progress before models fully converged. Those choices can bias you toward thinking bigger is always better, even when the data is too small. The DeepMind team re-examined the trade-off by varying both size and training tokens and by matching the learning rate schedule to the planned number of tokens.
That makes sense. How did they study it in detail?
They used three complementary methods. First, they trained families of models across sizes, and for each size, across multiple training horizons, then took the best achieved loss for a given compute level. Second, they traced what they call isoflop profiles, fixing a compute budget and sweeping over model size and data to find the loss valley. Third, they fit a simple formula that predicts loss from parameters and tokens, then solved for the best point under a compute constraint. All three approaches told the same story. Under fixed compute, grow parameters and data together.
When you say grow them together, can you give me a plain rule of thumb without lots of numbers?
A handy guideline is around 20 training tokens per parameter at today's scales. It's not a hard rule, but it captures the idea. If you double parameters, plan to roughly double the number of tokens to stay compute efficient.
That's practical. How did they test the idea at large scale?
They ran a head-to-head validation. Instead of making a bigger successor to Gopher, they trained Chinchilla with fewer parameters, but fed it many more tokens. Importantly, the total training compute stayed about the same, so it's a fair comparison. Then they evaluated both models on common language benchmarks.
And the result?
Chinchilla generally won. It achieved lower language modeling loss and higher accuracy across knowledge and reasoning benchmarks. The key point is not just that it performed better, but that it did so while being smaller, which lowers inference cost per generated token.
That runtime advantage matters for anyone deploying a model, not just training it.
Exactly. A bit on experimental design because credibility lives there. The scaling law fits came from many smaller and mid-scale runs that spanned a grid of model sizes and training token counts, with schedules matched to each data horizon. For the big validation, they kept the architecture family consistent and mainly reallocated compute from parameters to tokens. There were a few practical differences, like using Atom W as the optimizer and a slightly different tokenizer normalization, but the headline change was the compute allocation.
Do changes like the optimizer or tokenizer muddy the comparison?
They can influence results at the margin. The authors note those differences and argue they don't account for the overall gains. The consistent improvements across many benchmarks support the claim that data scarcity, not parameter scarcity, was the main bottleneck under fixed compute.
Before we move on, could you give a human-readable summary of the results without a long string of numbers?
Think of it like this. With about the same training compute, the smaller but trained longer chinchilla outperformed the larger but undertrained gopher on most tests. It read better, reasoned better, and recalled facts at least as well, often better. That pattern held across different evaluation styles.
What's the author's interpretation?
Their view is that the field focused too much on parameter count and too little on data. Feeding a model enough tokens to fully realize its capacity brings bigger gains than simply scaling parameters. In practice, many labs could do better by rebalancing budgets toward data collection and longer training, not just chasing the largest model.
Every good paper has caveats. What should listeners keep in mind?
A few things. At the very largest scale, the decisive comparison is essentially between two flagship runs, gopher and chinchilla, so more points on that curve would help. The exact training corpus mixture isn't fully public, which makes replication hard and raises data transparency questions. Because chinchilla saw much more data, there's also a reasonable concern about potential test overlap in pure language modeling benchmarks, though the authors emphasize evaluations that are less likely to leak. And yes, some engineering choices changed between the two models.
So the story is strong, but not beyond scrutiny. That sounds fair.
Agreed. For practitioners, start with the compute you truly have. Pick a parameter count you can train thoroughly, and plan roughly around 20 tokens per parameter, then tune from there. Match the learning rate schedule to the number of tokens you expect to see so the model converges properly. And consider total cost of ownership, not just training loss, because serving costs often dominate.
How might this generalize to other architectures like mixture of experts or retrieval-augmented systems?
The analysis here is for dense transformers. Mixture of experts can reduce inference cost by activating only parts of the network, which may shift the sweet spot. Retrieval adds information at inference time, which can reduce how much memorization you need. The general lesson still holds: match capacity with enough data and training time to use that capacity well.
What future directions would you highlight?
5 stand out. Fill in the compute frontier with more intermediate large-scale runs. Study multi-epoch regimes on smaller but higher quality corpora. Increase data transparency and deduplication for cleaner benchmarking. Extend the analysis to mixture of experts and retrieval-augmented models, and make decisions using total cost, training plus inference, not just pre-training loss.
I like that last one. Plenty of teams feel inference costs every day.
One more practical note. Because the recommended balance often lowers parameter counts for a given training budget, it reduces the barrier to entry. Labs with fewer accelerators can still reach competitive accuracy if they invest in data and allow training to run longer. It's not a promise, but it's a realistic implication.
Before we close, could you restate the TLDR for anyone who just joined?
Sure. Under a fixed training compute budget, scale model size and training data together. A smaller model trained on more tokens can outperform a much larger one trained on fewer tokens and will usually be cheaper to serve. The evidence is strong, with reasonable caveats around reproducibility and data transparency.
Clear and concise. Thanks, Ethan. I learned a lot.
Glad to hear it. This has been AI Podcast. If you found this useful, share it with a colleague planning a training run. Until next time, stay thoughtful and keep your models well fed with data.